So a lot, a lot, a lot of times in calc, we've been working through things. We've had rates. We would have found the speed, acceleration, and stuff by finding the first derivative, second derivative, correct? And that was at times where our functions aren't linear, and there's different things going on. So seeing the chain rule can be used to find dy dx implicitly. So another important use of the chain rule is to find the rates of change of two or more related variables that are changing with respect to time. So for example, when liquid is drained out of a funnel, the volume in the container, the radius of the liquid level, and the height of the water level are all functions of time. They're also related to each other. So if we think about it, you have a funnel, okay? So it's filled up. Right here's our water level when we start, okay? So there's a volume within the funnel, there's a radius within the funnel, and there's also a height in the funnel. Do you agree? Now, if we go to here, everything has decreased, right? Did everything decrease at the same time though? I mean, let's talk about a funnel. As a funnel goes down, it drains quicker, doesn't it? Because there's less liquid, it's less wide. As it comes down, it's kind of consistently getting smaller in radius, but the volume is drastically getting less and less. See what I'm saying? So we have a couple different things going on at the same time. I'd say one's pretty consistent, the other two aren't necessarily consistent. So we have to be able to take those relations and figure out something else based off of one speed, for instance. Okay? So this is just a very kind of rudimentary one here. We don't even have an example with it. I'm just gonna say here's some function, here's what's going on. We just want to look and see what it does for us. All right, so we have suppose x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. We want to find dy dt when x is 1, given that dx dt is 2 when x is 1. All right, so we want to find out after, call it maybe 1 second. After 1 second, what's happening, given that the other speed that's related has a speed of 2 at 1 second. All right, so we have our equation, y equals x squared plus 3. All right, so we're talking about speeds, we're talking about rates. Let's differentiate both sides of this. And we want to find dy dt, so we'll go ddt for both sides. All right, so left side, well, that's a y, so I'm going to have dy dt and it's gone, right? Derivative of y is just dy dt. Usually it was dy dx, now we just have t. All right, on the other side, looks like what, 2x? All right, now in this case though, everything is in with respect to t, right? So this would actually be 2x dx dt. So we have to kind of keep track of your letters here a little bit. So we're looking for dy dt. dy dt is already by itself. Okay, I found what dy dt is. It's 2x dx dt. So what I need to do then, I can plug in what I know. So dy dt is equal to 2. Now x, we talked about x. We want x equal to 1. So we put a 1 in. And then we also already have dx dt at that time, which is 2. Okay, so in that case, left with 4. So the speed of that function would be 4 after 1 second, given that the other one that's related to it has a speed of 2. And again, we don't really have an explanation for this. It was just to see what it kind of looked like in a very rudimentary, simple form. All right. Now, I got that stuff on the right. We're just going to ignore that for now. The equation given rate find. We're going to ignore that for now. Let's look at this next thing first. So here's some guidelines for solving related rate problems. Okay, you want to identify all given quantities and quantities that are to be determined. We're going to label the quantities, and we want to draw a picture if needed. Okay. Second thing, we want to write an equation involving the variables whose rates of change either are given or are to be determined. 3, we want to use the chain rule, implicitly differentiate both sides of the equation with respect to time t. And then after step 3, substitute back in the stuff you have and solve anything you might need. All right. So if we go back here again, based off of what we were just given here, we want to take that process and apply it to this problem. So first off, what were we given? We were given that equation. Sometimes you have to come up with the equation yourself. Okay, that's what we were given. Our given rate was our dx dt was 2 when x equals 1. All right, and we were looking for dy dt when x equals 1. So this is a really good first step anytime you go to do one of these problems. Just take a second, identify all your items. That way it's kind of neat for you. All right. Now sometimes you're going to be given the equation, you're given a rate, you're looking for, you're finding something else. Sometimes you have to find the equation first. Sometimes you have to, it varies from problem to problem. So we're just going to look at a couple different types of problems now. All right. Any questions on that first one so far? All right, so the next one. This is a very common related rate problem. There's ripples in a pond. So a pebble is dropped into a calm pond, causing ripples to form in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? All right, so drop the pebble, and this is concentric rings, right? So we're worried about this outside ring here. We want to relate its radius with the speed that the radius is changing versus the rate at which the total area in there is changing. All right, and then we want to find it for a certain time. All right, so do we have any given rates? Do we have any equations, first off? We don't have an equation given. All right, kind of stinks, but all right. So given rates, do we have any one of those? We have 1 foot per second, right? Now what is that? That's the rate of the radius, correct? So that would be, we'll call that dr dt. The radius is rate with respect to time. And we'll say that's 1. Okay. What are we looking for? Well, we want to find it with the area, right? We want to find the area, so we'll call that dA dt. That's the area with respect to time. And we want to find it at 4 feet. So we want to find dA dt when r equals 4. Now we're still hung up a little bit. We still need to find an equation of some sort, don't we? What's one equation you could think about that relates radius and area to a circle? Yeah, pi r squared. The area formula. Area equals pi r squared. So now I have an equation that has both variables in that I'm working with. I'm looking with radius, I'm working with area. Area, radius. So that was when we had to supply our own equation. All right, so let's take that equation we just worked with and let's differentiate both sides of the equation with respect to t. All right, so left side, derivative of a is just going to be 1, and that would be dA dt. The right side, we apply our rules to that. Pi is basically a constant, so we can just take the 2 out front. So it'll be 2 pi r. Now we just did this as dr dt. Okay. Now I'm looking for dA dt, correct? So I differentiated both sides implicitly. Is dA dt by itself? Yeah, it is. So I'm in good shape. So now I can take that rate that I just found, and I can plug in what I know. So I have 2 pi r. Well, I'm worried about when the radius is 4. So we'll put a 4 in there for the radius. And we know the given rate of the related rate, correct? Given rate is 1. dr dt, dr dt. Plug in a 1. 2 times 4 is 8. You got 8 pi. Multiply that out. Leave it as 8 pi, or it could also be, would it be about 25? About 25 feet squared per second. So if the radius is changing 1 foot per second, the area is changing about 25 feet per second at that given time. That make sense, guys? Okay, let's try to inflating balloon. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when find the rate of change of the radius when the radius is 2 feet. All right. So we're given a rate right off the bat, aren't we? 4 cubic feet per minute, and that would be what? Cubic feet. That'd be volume, wouldn't it? All right. So this would be volume. So I would have, we'll call that dV dt. So our dV dt is 4.5. I'm going to make that 9/2, just because that's going to be a little easier on us. You all right with that? It's 9/2 fraction works a little better than a decimal. Okay. Now we want to find the rate of the radius. So we want to find dr dt when our radius is 2. All right, can we think of an equation that would relate volume and radius? Remember the volume formula? Don't remember the volume formula for a sphere? All right, I'll help you. Volume is 4/3 pi r cubed. I thought maybe you remembered it. Back from your geometry days.
That was 2 months. 2 years ago.
All right, so we got that. Sometimes in those problems, they'll give it to you. Be like, hey, reminder, this is the volume formula, and so on and so forth.
You better.
All right, so let's take this guy, differentiate it. So we're going to find ddt of v equals 4/3 pi r cubed. All right, so on the left side, I'm just going to have dv dt. On the right side, I would have 3 from the power rule. I'd have 3 go out front, right? So that'd be 12/3, which would be just 4, right? 4 pi r, and then the power rule out front, subtract 1 pi r squared. Now I just differentiated that with respect to r, because that's the only variable that was there. So I have the dt there. All right, now which one am I looking for? I'm looking for dr dt, correct? So I'm going to have to divide both sides by this, correct? Divide both sides. So I'm going to end up with then that dr dt is equal to 1/4 pi r squared dv dt. I just kind of flipped it. I divided both sides by 4 pi r squared. So I multiplied both sides with their reciprocal. That's where I got this at. And then technically this should be on the right. I just flipped it around. You with me? Okay. All right, so I got that. Now I'm almost there. Do I know my radius? Yeah, I know my radius is going to be 2. I know dv/dt is 9/2. So let's plug in what we know. So that's going to be equal then to 1/4 pi r squared times, sorry, I got 2 there I can put in, times 9/2. Now I put that in a calculator. If you want to trust me on that, it'll be 0.09 per minute. And that would be every minute it's increasing by 0.09 feet. All right, still with me?
Yes. Really bad.
It's really slow, yeah. 4 cubic feet a minute, that's not much at all. All right. If we can get through 2 more, I'm going to be happy. I might only get through 1.
Just stop overhead.
Actually, I'm thinking I might do 1 and stop right there. Put the last 2 on a separate video. You guys all right with that?
Yeah.
All right. So let's do speed of an airplane tracked by radar. An airplane is flying on a flight path that will take it directly over a radar station. If S is decreasing at a rate of 400 miles per hour when S is 10 miles, what's the speed of the plane? There's a lot of stuff going on here right now, isn't there? Okay. So let's see. What do we know? Well, S is 10, and we have a rate there too, don't we? Yeah. So we have what would be, say it's S is 10, say the SDT is going to be 400 when S is 10. So we know that. Now, it's also decreasing, correct? Okay, it's decreasing at a rate, so we'll say that's negative 400. All right. Now, we got to do a little more work here. I'm going to draw this picture. This picture would be supplied. We have a plane. Here's the radar station. Okay, the plane is flying this way. All right, so I just made a right triangle here, didn't I? And I'm worried about, so the path that's looking at it, this would be my S here. Okay, that's changing at a different speed than the plane is changing, obviously. All right, now, if I want to find the plane speed, I'm going to have to worry about this distance over time. All right, and then we also know, do we know anything else? All right, in the picture, it says it's 6 miles overhead. Okay, so there's everything we know. All right, now looking at this, I almost have the Pythagorean theorem, don't I? Got one side, I have variables for 2 others. And if I peek over here to the side, I have the value for S, don't I? So if I say that S is 10, then I have 6 squared plus x squared equals 10 squared. All right. So then that leaves me with, what, 100. It's going to be minus 36 and the square root of that. That's going to be 64, which is 8. That was just from the problem. That was given in the picture. Okay, so that'd be a given too, that the plane is 6 feet or 6 miles overhead of the radar station. All right, so I want to find the x dt find it at 2 different times. Bless you. I want to find it when S is 10, and I also want to find it when X is 8. If I do that, then I can find whether it's consistent or not, right? Now, also at the same time, remember when I came up with this thing here, that was a way to relate the two together, wasn't it? I mean, I put in a 10, but that was just S. Can I use this as my equation? Yep. X squared plus 6 squared equals S squared. Good, Funk? All right, so let's take that equation. Let's differentiate that and then plug some stuff back in. All right, so I want to find d dt of x squared plus 6 squared and equal to s squared d dt. The left side is going to be pretty easy. I mean, it's 36. 36 goes away. I'm looking at 2x and then dx dt. All right. And then on the right side, that's just going to be 2s. That would be ds dt. So I'm looking for dx dt. Okay, so that's the plane. All right, I'm looking at the distance he flies over that time. So I'm looking for dx dt, so I'm going to divide both sides by 2x. That's going to give me that dx dt is equal to s over x times ds dt. All right, still with me? Now, I'm going to take this next one here. Okay, I need to find, I have my ds dt of negative 400 already from up here. Okay, and that's when s was 10. Well, we're looking for the speed with s is 10 and x is 8. All right, so we're going to add that together, and I'm going to go with, and I'm going to have 18, sorry, not 18, 10. 10, 8. Okay, so I have 10 over 8, just plugged in for s, plugged in for x. 10 over 8, multiply 10 over 8 times negative 400, get negative 500. Okay, so how fast? Plane flying. 500 miles per hour. Why is it negative? Why is it negative? It's not going down. It's going this way. It's going flat. But the distance away from the station is going down. Is that what you're trying to mean? Because here's the location, right? It's flying. It's not landing. It's flying overhead. Plane's flying this way. This distance is decreasing. Because when it's straight overhead, it's 0 miles away. This was the distance here that we're marking. This is our ds dt. Okay? So when I'm looking out, it's changing. As I'm standing here, think about it. I'm looking at the plane. It's 400. This distance is changing. But that plane is flying on a straight line, and it's flying at 500 miles per hour. So I have this going on. See, there's 2 different speeds. So that plane is 500 miles per hour. All right? These are tough. I'm not going to lie to you. These are tough.
Didn't we do something like this last year?
We'll stop right there.